Hi, my name is Fernando Ramos Diaz. This summer I worked on Rabi oscillation and precession with Professor Irinel Curescu. This precession was plotted on a Bloch sphere. The Bloch sphere is very similar to a qubit in that it has an on and an off state, and it maps things very well because if you have any vector upon that Bloch sphere that isn't on the top or the bottom, it can be very well described in polar coordinates as a superposition known as phi right here. The precession that we were looking at initially was Larmor precession, which is the simple precession of a magnetic moment about a magnetic field. But we added in a microwave field in order to create a Rabi oscillation. Now, Rabi oscillation is the addition of two oscillations shown in figure A. But once we get into figure B in the rotation and the rotational frame, we see how simple that value actually is. Think about the oscillations adding up as two vectors add up to one another. Now, since we were plotting in Q-tip, we needed to plot the actual Hamiltonian of the rotating frame. That just makes things easier and more clear to see. But that Hamiltonian is written in the red box, where the initial Hamiltonian of the laboratory frame is in the blue box. If anyone has any questions, feel free to email me, but don't have time to get into this right now. Now, Q-tip, as I mentioned, is Quantum Toolbox in Python. It's a very helpful software that allows us to plot Bloch spheres quickly, and it shows the trajectory and really lets us run simulations very easily. What we got out of this is that we actually were able to get the eigenvalues of that Hamiltonian of the rotating frame to be described in terms of delta and H, where H corresponds to the microwave field kind of strength, and then delta is the difference between the two frequencies of the static field and the microwave field. Now, further, if we take the two eigenvalues and take the difference between them, we get the Rabi frequency, which is the frequency at which the spin rotates in the microwave field in the rotating frame. This is important because of quantum gates. So in the figure here at resonance, 1 pi gate corresponds to the full, the rotation from here to here to 0 to 1 state in half a period. Now that value, or being in that on and off state, can be tweaked by resonance values. And that's important because we can just really fine tune what value we want after a full pi gate. Now, in order to see how effective that is, we have to look at the decoherence values or dephasing. This just signifies how much the microwave field needs to be increased in order to go through that quantum gate or through that rotation. Yeah, if anyone has any questions, go ahead and email me.